Welcome to class this wonderful Friday. I hope everyone is well. We are going to start today talking about capacitors and capacitance. And what you will find when we go through this today is it's like many things in this circuits class where it's going to have a feel of being somewhat familiar now that you have seen some of the stuff that we covered about inductors. In electrical engineering, there are all kinds of places where you end up seeing things that are called duals of one another. So you'll see like nodal and mesh. They kind of have very similar feel to them, and it's because nodal and mesh are duals of one another. So we're going to see something today where we've got capacitors and inductors, and those are also kind of duals of one another. So some of this will start to feel a little bit familiar when we go through this. And we are going to do an example problem at the end that is a little different so that we can see just another kind of aspect of something that can be dealt with these style of problems. So without further ado, let's talk about capacitance. So it turns out that when you have two plates of conductive material, and they don't necessarily even have to be plates, I would just say when you have two pieces of conductive material that you bring close to each other but that you do not connect, so they are insulated from one another, but you bring them somewhat close to each other, there is an effect that starts to happen where there's this electric field that builds between the two plates. And let me show you how that happens with this little picture that I'm showing up here. So let's say we put a voltage source that's connected across these two plates, and as a result of that voltage source being put on there, it means that, let's say you start with zero charge built up in the capacitor that I'm representing with these two plates with some kind of a medium in between the two plates. That's what the yellow is that you're seeing. Anyway, before you hook up this power supply, there's zero charge in this, between these two plates, and then you hook it up, and what happens is a little bit of current starts to flow this way. I'll call that I. And it might be helpful at this time to kind of think of what does that actually mean probably physically. What that probably means physically is that there is a flow of electrons actually that is going the other way. This is one of the only other spots in this course where I'm going to mention electron flow as opposed to just traditional or conventional current as we call it sometimes. So if electrons flow this way, that also means electrons end up flowing this way. And what that ends up doing is it ends up putting a kind of a surplus of electrons on this plate down here. You end up with all kind of these negative charges, right, down here on this plate down here. I'll just draw a few of them in like that. And what this has also done is it has taken electrons that were on the upper plate and it has sort of bled those off. By pulling those electrons out of that plate, it means that the material in that plate now is going to be positively charged, right? So you're going to have this kind of positive charge built up on this upper plate as a result of those electrons being driven with the voltage source more from the top plate to the bottom plate. And as this goes on, a few other things happen. One is there's an electric field that builds between these two plates, all right? And that electric field that builds between the two plates is going to store energy. In that way, it's kind of similar to the inductors that we saw when we met last time, that it stored energy in a magnetic field. The capacitor stores energy in an electric field, which is a different kind of field than a magnetic field. All right? And there's a couple different ways that this actually occurs. One of them is that the material itself between the two plates, it can actually have certain orientation for the little particles that make up that material. They can actually sort of flip and sort of line themselves all up into kind of this chain of electric charges. That's kind of how that electric field gets stored. But I should say that's not the only way that that can occur. The other thing that can happen is that this electric field can build even if this thing is in a vacuum. So it doesn't need a medium between the two plates in order for it to, essentially still be able to store energy in an electric field between the two plates. I'm going to give you one little equation here that helps you understand some of the parameters that matter with respect to making a capacitor. And this is the equation that I'm going to show you. The capacitance that you have for a parallel plate capacitor like this one is going to be equal to a parameter that we denote with a little epsilon. That parameter is called permissivity, and it's a material property of the medium that is going to be between the two plates. This is going to be multiplied by the area of the plates. I've got that kind of indicated there as A, divided by the distance between the two plates, D. All right? So if you think about the types of things that matter with respect to increasing the capacitance of a capacitor, right? One of those is cross-sectional area of the plates, like how much parallel area do you have between the two conductors that you're trying to bring close to each other. If you increase that area, what does it do to capacitance? The capacitance increases. That's right. They also do some things with different kinds of material that might have higher values of permissivity, right? You can only get so much out of that, but there are some efforts that are done to try to figure out how you can increase your permissivity so that you can have a certain amount of capacitance for a relatively, hopefully, generally, you're trying to make your package smaller for how big your capacitor is. That's usually the goal. But what else can they do to try to increase capacitance without having to try to increase package size? Okay? If you can decrease the distance between the plates, that has an effect of increasing capacitance. Okay? Does that have a limit, do you think? And if it does, what limits how close you can put those two plates together? Yeah, it does have a limit. What we sometimes call that limit that would keep you from being able to put them too close to each other is it needs to have a certain what's called dielectric strength. What do you think that means? That's a big fancy term. Okay. Ability to prevent conduction, very well put. Okay. It's essentially how strong, how much voltage can you put between the plates without there being some kind of current that still finds its way through what you thought was essentially an insulating medium, right? So that if you have a medium that is better at preventing current from flowing, that has a higher dielectric strength. So usually, how much dielectric strength you have improves as you increase the distance between the two plates that are trying to conduct, and for that reason you can't necessarily get them infinitely close to one another because that usually has the effect of decreasing dielectric strength. All right, so there are limits on that. That's basically what I'm saying. So anyway, in terms of the physical construction of a parallel plate capacitor, this is instructive to us because it helps us to know what parameters matter with respect to making a capacitor that might have a higher value versus a lower value. Okay? Here's the other equation that kind of matters with respect to capacitors, and it is this. You might remember a long way back we talked about the letter Q. Do you remember what we used the letter Q to describe? Charge. Okay? Charge is actually related to capacitance as well. It is just going to be equal to the capacitance value times the voltage across the capacitor. All right? This is essentially the amount of charge that has built up in the capacitor is Q. C is the capacitance value, and V is the voltage across the capacitor. So those are kind of the two equations, and really the one that we are going to start from with respect to most of the circuits analysis stuff that we do is going to be this one, that charge is equal to capacitance times voltage. I did want you to have an idea as to what real capacitors actually kind of look like as well, and that's why I put these pictures up here. Interesting thing about capacitors, they can range in size from incredibly tiny up to quite large. The other thing I'll say is that the units of capacitance, which I'm going to talk about here in just a second, the basic unit of capacitance is called a farad, but a farad is a large amount of capacitance. 1 farad is a very, very large capacitor. Matter of fact, that's what I'm showing you over here on the left, this big black capacitor that has a little number indicator on there. That is a piece of equipment that they put into stereo systems a lot of times automotive stereo systems need some kind of a storage of energy so that if you have these speakers hit real hard, it can actually supply that energy quickly. And that's one of the uses that people find for capacitors, is they generally have the ability to deliver energy at a very, very high rate if they need to, but they don't store that much energy. All right, so whenever you use these in a stereo system, that's essentially what you're trying to do, is you're delivering energy from the vehicle, but the capacitor is there to try to smooth out that energy delivery. If it needs high amounts all at once, it's there to kind of supply those over very brief periods of time. Okay? Anyway, there are other types of capacitors as well. These yellow ones that I'm showing you here, those are fairly small, kind of maybe about the size of a match head or so. This one that you see right here is one that is designed to be soldered onto a circuit board, and they range in size. You know, those little ones right there are kind of like these guys right here, but they range in size higher than that as well. Okay. Quick comment, if you want to buy that 1 farad capacitor, it's about 35 bucks. All right, in case you're interested in trying to make a purchase to put into your, sound system that you're trying to do. And before I leave this screen, I'm going to make one other comment about capacitance. I didn't necessarily lead this lecture like I did with the last one, where I talked about the physical analogy for like a flow loop circuit for inductance. But there is an analogy for this as well. Capacitance is often thought of as electrical elasticity. And so, it's like a spring or like a little pressure chamber in a fluid system or something like that. That's sort of the analogy that you would have for a capacitor, is something like elasticity. Okay? And we're going to see kind of how those equations work here in just a second. All right, there is another quick point I need to make about real capacitors as well, in that there are some types of capacitor that are polar devices. And what we mean by that is that matters which direction you hook up your capacitor into a circuit. Okay? The main family of capacitors where this matters is called electrolytic capacitors. And so I wanted to talk about these for a little bit, because electrolytic capacitors, they have kind of that disadvantage, I would even call it, in terms of being polar, meaning you can only really connect voltage across them reliably in one direction and not in both directions. That's kind of a disadvantage, but they have a very big advantage in that they typically have some of the highest capacitance values per package size of any of the kind of options that you have for various kinds of capacitors. And I wanted to show you the reason why that is. Okay, but we have to get into how an electrolytic capacitor is built. The way they build these things, kind of the essential idea is, instead of having like a layer, let's say, of some insulating material, that, let's say you have like a piece of conductive material, and then you have a little film of insulating material, and then another piece of conductive material. Instead of thinking about it like that, with electrolytic capacitors, they are built in a way that, there's a property of aluminum in particular, that if you take aluminum and you do a process that's called anodization, okay, what that does is it forms a very strong and impermeable oxide layer on the surface of the aluminum. And what's interesting is that oxide layer that forms when you anodize aluminum is an insulator. Aluminum oxide insulates, whereas the aluminum itself is a conductor. And this is why it matters for these electrolytic capacitors what polarity you put on them, is that when I say the word anodization, that word means, it carries with it this idea of being an electrode that has one of the two polarities. Turns out it's the positive electrode, that you put positive charge on that electrode, and what happens is that's the electrode that the aluminum oxide is going to form on. And as that happens, if you keep using that capacitor in that polarity, what will happen is that oxide layer will continue to strengthen. Right? It probably starts out where they oxidize it before they ever put it into the capacitor, but if you keep polarizing the capacitor in that direction, it will continue to strengthen that oxide layer in the event that any current actually flows. But what will happen is the oxide layer will build itself up to the point where it insulates more or less perfectly, and the current won't keep flowing, and so it won't keep anodizing. That anodization process will end as soon as it becomes a good, a good insulator. All right, does that kind of make sense? And so what you're seeing here is that you have usually a conductive material that is the cathode of the aluminum. That's kind of the green plate that you have right here. It interfaces with a piece of paper that is all soaked in, I'm going to just, this probably isn't exactly what it is, but it's something like salt water. It's an electrolytic, it's a wet electrolytic piece of paper, okay? And it's wetted down with something like salt water, like an electrolyte. And then that essentially carries the effective electrode all the way up to the surface, right? All the way up to here. That is all the electrode that's connected to the positive terminal, right? And then the oxide layer is this little gray piece right here in the middle. It's insulating. And then you have your, sometimes they call it elemental aluminum, right? That is the positive side over here. And that is the side that is the other electrode. The big advantage here is that that little layer of oxide is so thin that when you look at that equation I talked about just a minute ago, right, that capacitance is equal to your permissivity times the area over the distance between the two electrodes. With an electrolytic capacitor, you can take that D value and make it extremely tiny because all it is the thickness of the oxide layer. That's how thick or how far apart the effective electrodes are in an electrolytic capacitor. So anyway, I wanted to talk about this because it matters what orientation, sort of what polarity you plug in an electrolytic capacitor, because if you orient it the wrong way, what will happen is that anodized aluminum that you have on the one electrode, it will start to break down and it will start to allow current to flow. And if current flows, eventually it's like if you keep putting voltage across it, it becomes like a short circuit. And if it becomes like a short circuit with voltage across it, what happens then? Okay? At that point, you don't have zero power delivery. You have some non-zero power delivery. It couldn't be very high power delivery. Where does that go, that power? It goes into the capacitor. Remember, the capacitor is filled up with some liquid, right? So it will boil that liquid. And you know what will happen then? Okay. It's actually kind of cool. I had a professor when I was in school that actually purposefully popped capacitors by polarizing them the wrong way so that we could see what would go on. It turns out that this little, if you look at the top of this little canister of this capacitor right here, see those three lines right there? You know why those are there? Those are there because if they are not there, then the little end of this capacitor, instead of, let's say you boil that material, you boil that liquid inside of there, it's going to have to expand, right? One way it could expand is by taking the little top of that capacitor and shooting it across the room and making a little projectile. So they put these little weak spots in the little cap of the capacitor so that instead of doing that, it essentially purposefully breaks those and it lets the pressure out in an alternative way. Yeah, I know. Some of you are disappointed, right? You wanted to see the top of the capacitor fly across the room. It turns out that some people don't like high amounts of liability. And so, the companies that make these determine that may not be the best way to make them to where they would make little projectiles. All right. Yeah, do you want to make your own? I can't stop what you do in your personal life. But I don't think we're going to do that in this class. All right. I think that's about all I have to say about electrolytic capacitors, but it's interesting stuff. They are a good way of getting a high amount of capacitance in a fairly small package. And again, the main reason why is that low value for that distance between the two conductive plates, if you will, that form the capacitor. All right, let's get into the stuff that might be even more, I I guess, relevant to what we're going to do in this class. The first thing is we need to start defining some mathematical relationships about how capacitors work. And, I mentioned this earlier, but the starting point that we're going to have for this is that charge in a capacitor is going to be equal to the capacitance value times the voltage across the capacitor. Now, most capacitors are not built in a way that you expect for their capacitance to be time dependent, right? If you think about the equation I gave you a minute ago, where capacitance is equal to permissivity times area over distance between the two plates, usually none of those parameters really change with time. So we can generally take the C value that we think about here and think it is not time variant, okay? Once I do that, what can I do with both sides of this expression that might have something to do with time? Give me an idea of something we could do with both sides of this expression. Could I take, for instance, a derivative of both sides of the expression with respect to time? Okay, yeah. What I have on the left side when I do that is dq dt. This is going to be equal to, remember, C is not time variant, or we presume that C is not time variant. So that just becomes a constant times what? dV dt, which is the time rate of change of voltage across the little capacitor. And just to kind of make sure we know what we're talking about here, let me draw a little symbol that represents a capacitor. This is how we're going to typically draw these, is with a little kind of two parallel lines next to each other with the two electrodes that come out. And I'm going to say the voltage across this capacitor is V, okay? And the capacitance value of the capacitor is C. So this is often how we will draw a little sketch of what a capacitor looks like on a circuit diagram at least. Okay, so what is dq dt? What is the time rate of change of charge? Current. That's right. This is like a flow rate. It's the time rate of change of charge. And when we draw that, we're basically going to draw it this direction, where the charge I, or excuse me, the current I goes this direction. And so what we can rewrite this as is that I is equal to C dV dt. Okay, and that is an equation that I would like you to commit to memory. Okay, now to help you out with committing that to memory just a little bit, there was an equation last time I asked you to commit to memory as well. Do you remember what that equation might have been? It's not committed to memory yet. You still have some time before the next exam, I suppose. Okay, here's the one I asked you to remember last time. V was equal to L, what? di dt. Okay? Okay, so this is something that you should remember from last time. And I want you to look at those two equations pretty closely. Can you see why we might have a situation where we have duals of one another between capacitors and inductors? Okay? With capacitors, the current that flows in a capacitor is equal to the capacitance times the time rate of change of voltage. In an inductor, the voltage is equal to the inductance times the time rate of change of current. So they're essentially sort of inverted from one another in terms of how they work. And it's kind of interesting to realize that. Let me make a quick note here about units. Okay, so to start off, let me rewrite my equation that I had right there, where I just isolate C on one side. So C is going to be equal to I over dV dt. Agree with that? Now let's think about what those units would be, particularly in something like an SI system or something like that, your typical units for each of these values. What would you have there? Okay, so you would have something like amp for I, and then in V dV dt there, that would be something like V volts per second. Okay? With me so far? Now let me ask you this. Is what I just wrote there equal to seconds over volts per amp? Okay? All I did there was I just sort of rearranged it, right? If you put something in the denominator that is in the denominator, right? So like seconds is in a denominator of an expression that was already in the denominator, that's sort of like you can move it to the numerator, right? But you can also go the other way and move amps down to the denominator of the denominator, right? And that ends up giving us this expression of seconds over volts per amp. Okay? Now what does that mean? Or can we do anything more with that? Okay? Seconds per ohm. Okay? Seconds per ohm is the essence of what a unit is for capacitance. But like many things, we don't leave it there. We are going to give that a name. Okay? A farad, okay, which we denote that with the letter F, is equal to a second per ohm. All right? Cool. So that's kind of how we relate, current relative to voltage for a capacitor. Now what I'm going to do over here on the right side is, can we relate voltage relative to current instead? Okay, we probably can. How do we go about doing that? Probably the first step is to sort of rearrange our equation a little bit, and here's how I'm going to start. I'm going to say, let's say we say dV is equal to 1 over C times I dt. Okay, would you agree that I can rearrange the expression that I started off with over here into dV is equal to 1 over C I dt? Okay, now a quick thing I want to do here really to emphasize it is I want to say that both voltage and current, we presume those are functions of time, right? We presume that those can change and vary as time moves on. And so instead of just saying I, to really emphasize it, I'm going to put here I of t, to emphasize that I is a function of time. Okay? Now that I've put that expression up there, what do you think I might do next? Okay? What if I integrate both sides? And if I integrate the left side, I would want to do that from a voltage that I would have at one time to a voltage that I would have at another time. On the right side of the expression, let's go back and remember, does C vary with time? The capacitance itself, does it vary with time? No, that's a constant value with respect to time. So I can leave the 1 over C outside of the integral expression that I'm going to write on that right side. So I can write that integral over here. And over there, I'm going to let t vary from the same two time values that I indicated we would have voltages over on the left side, right? The voltage at time 1 and the voltage at time 2. On the right side, we're just going to take time 1 and time 2. All right? Now, what does that mean I end up with on the left side of my equation? Okay. The voltage at time 2 minus the voltage at time 1 is all I end up with on the left side of the equation. What about on the right side of the equation? Okay. Really nothing changes, right? That's as far as I can go until I have something more about the nature of the relationship for my current, right? Current relative to time. Okay. So I can just leave that alone on the right side. 1 over C, integral from time 1 to time 2 of I of t dt. And that is the relationship that we have, but if you want to get voltage and you know current, it involves taking that integral. Now let me give you another little format that we sometimes use for this same expression. The one I gave you here assumes that you're starting at some time that is not necessarily zero, some time value that's not zero. So in a sense, this is the most powerful version of this equation that I can make, because it goes from any time to any new time, right? You start at one time and you go to another time. But a lot of the problems that you work will be set up so that the initial time that you use, and in this case that would be t1, right? The initial time value that you just go ahead and select is you say, I'm going to count my initial time as time 0. Okay? And if you do that, this equation ends up just a little bit different. And sometimes this is what you say, is that the voltage at some time is equal to the voltage at some initial time, which you can express that with V at 0, plus what? 1 over C times the integral from 0 to that time value that you're trying to figure the voltage out, figure out that voltage at, of I of t dt. Okay? Now, here's a quick thing that I need to note when I write this expression up here. The t that I put up here in the numerator, or excuse me, not the numerator, the upper limit of integration. Okay? The t that I put up there is not necessarily the same as the t that I put inside of the integral. Okay? If you remember, you may have touched on this in a calculus class or something like that. Inside the integral, the variable that you use there is important because it helps you to actually manipulate things. But technically, the variable that's inside of there is what's called a dummy variable. Meaning I could use any symbol I wanted to where I put t inside of the integral. Right? It doesn't really matter what symbol you put there. You just need something to move around as you manipulate and figure out what your integral becomes. Okay? So I just really should emphasize that the t that I have in the limits of the integration is the t that I'm putting in v of t over here, whereas the t that is in the I of t dt, that is a dummy variable, and so sometimes in some texts you'll see them replace that variable with some different kind of variable so that it emphasizes that it's a dummy variable and not the one that you're actually using. Does that make sense? Okay. I wanted to, while I'm here, I wanted to go ahead and supplement something I did with the inductor lecture, and that is you can make an expression for current in an inductor that is in this same format. Okay? Because you might remember I had an equation, I won't rewrite it up here, but I had an equation that looked kind of similar to that one where it came up with currents as a function of voltage for an inductor. You might remember, and it's essentially the same equation but with voltages and currents flipped and with an inductance value instead of a capacitance value. Okay? So I wanted to go ahead and tell you that for an inductor, I of t is equal to whatever your I value is at time 0 plus 1 over L, the integral from 0 to t of v of t dt. And again, the t that you have in the upper limit of integration is the t that you have as the argument that's in that I function on the left side, whereas the t that's inside of this expression is a dummy variable. Okay? Cool. So that's, that gives us another couple of forms of that same idea that we can use. Yes, ma'am? That L is what we have for inductance, right? What I'm showing you here, I didn't derive this just now. I'm just showing you, I'm supplementing from what we did last time and saying you can rewrite the expression that we got last time for current in an inductor given voltage. You can rewrite it in this form, and I'm kind of putting it in the same form as I just came up with for the capacitor. Okay? Cool. Now let's look at power and energy in a capacitor. All right? And I'm going to start by sort of listing some of the equations that we might know already. Okay? First of all, what's our basic equation that we typically use for power? IV. right? Current times voltage. Also, if you know power as a function of time, can you figure out how much energy, okay, energy has flowed? So energy is equal to an integral over some time of p dt. And I'll just express it there as an antiderivative. But, you know, kind of the same idea works there, that the amount of energy flow that you have is the power integrated over some time span. Okay? What other equations might matter for what we're about to do here? It's one that I recently asked you to commit to memory. But you don't have to just yet because it's still on the screen. Okay? Yeah, I is equal to C dV dt. Okay, so with these three equations, I'm going to try to come up with an expression for how much energy is stored in a capacitor. That's kind of where I'm trying to go with it. So first, let's talk about power, though. If I'm trying to make an expression for power, one of the things I can do is substitute in C dV dt for I that I had in my initial expression. So that means I'll have C dV dt. That is my I that I started out with P equals IV. But then I'm going to take this and multiply it by V. Agree with that? Okay. Now what happens if I take the power that I just came up with here and integrate it according to my energy is equal to the integral of power over time? What I'll have is the integral of C dV dt times V times dt. So what happens with my dt's? They cancel, right? What happens with C? C, remember, is a constant relative to time. It's also a constant, at least we presume it is, relative to voltage. We kind of presume that it's not changing relative to voltage. May or may not always be a good assumption, but we're going to make that assumption that capacitance is not varying with voltage. Okay? So that means we can pull it out, and that means that we've got C times what? Integral of V dV. When you integrate V dV, what does that give you? Okay? 1/2 V squared. Right? So what we put this together as typically is 1/2 C V squared. And this is the energy stored in a capacitor. All right? Does that look familiar at all? It does not look familiar? What if I wrote this up here and I said, remember that we had energy in an inductor Do you remember the formula we had for that? 1/2 L I squared. Now, one of the reasons I'm taking a special amount of purpose here to trying to show these is that it's my theory that if you have a number of things that look relatively similar, it's usually easier to remember them because you can form some sort of a mental structure around how the kind of all the things that you need to know, kind of where they belong and how they work, right? So the thing to remember about inductors is that it is essentially the current that is most directly related to the energy storage, right? Because it's the current that affects how big the magnetic field is in an inductor. And that's what is actually storing the energy. You increase that current, you'll increase the amount of magnetic field, and that's what's actually storing the energy. Okay? What about capacitors? Okay, with capacitors, if you increase voltage, that's what increases the amount of electric field, and that's what's actually storing the energy. Okay? And so because of that, the equation for how much energy is stored in a capacitor is related only to capacitance and voltage. Right? And for an inductor, the amount of energy stored in an inductor is only related to inductance and current. Right? But the forms of them are identical. And so that's kind of less stuff for you to have to remember. Okay? With me so far? Fantastic. Now you might predict what we might do next. Is it possible to take capacitors, and if you have like a more complicated network of capacitors, take that complicated network of capacitors and simplify it by using the concept of equivalent capacitance? Okay? As you might suspect, the answer to that question is yes. Let's look at the two different forms that are normally of most use to us when we do this, and that is, how do you collapse parallel capacitors, and then how do you collapse series capacitors? Okay, so let's start with a parallel case first here. And when you have a number of things in parallel with each other, how do the voltages across each one relate? They're all the same, right? They're going to have the same voltage across each one. So when I put V up here, that V is applied across every single one of these capacitors. Okay? So is everyone comfortable with that idea? Okay. Let me furthermore define a current that flows in each one of these capacitors. Okay? So I'm going to define three different currents. I'm going to call them I1, I2, and I3. Okay? And the equation that I just asked you to commit to memory not long ago was what? Okay? I is equal to C dV dt. That equation holds individually for each one of these capacitors. Right? So I can write three different equations based on this, what I've gotten written up here so far. One of them is that I1 is equal to C1 times what? Okay, I could say dV1 dt, but remember the voltage is the same across all of them, so instead of trying to define a new voltage like V1, I'll just say dV dt. Okay? dV dt. Okay, what other equations can I write? Okay, I2 is going to be equal to C2 dV dt. Right? I3 is going to be equal to C3 dV dt. All right? So far, so good? Now, in order for two circuits to be equivalent to one another, they actually have to have a relationship that matches between voltage and current, right? So if I put a voltage of V across my original circuit on the left, it's going to result in some kind of a current that I'm going to call I. How does I relate to I1, I2, and I3? Okay, Kirchhoff's current law says I is going to be equal to I1 plus I2 plus I3. Okay, and what's that equal to? It's going to be equal to C1 dV dt plus C2 dV dt plus C3 dV dt. What can I do with dV dt? I can factor that thing out, and I have that I is equal to C1 plus C2 plus C3 dV dt. Now here's my question. This kind of circuit I've been working with on the right, on the left, it has to have the same voltage and current relationship as the circuit that I have over here on the right. If I put V and I, its behavior has to be exactly the same as the original, if they're going to be equivalent. Okay? And I went ahead and labeled C as CEQ, right? To mean, if we can find this thing, that we're going to find this CEQ value that's going to make these things equivalent. One way of doing that is to just write the equation for that one. What would the equation be for that last capacitor? I is going to be equal to CEQ dV dt, right? I could formally equate these two to one another and then divide out the dV dt, but you guys can see how that would work, right? Equate those two together and divide out dV dt. This tells us that CEQ has to be equal to C1 plus C2 plus C3. And what if I had had more than 3 capacitors in parallel with one another? I could just add however many of them I have up to, let's say I have n of them, right? This is the equation for figuring out equivalent capacitance for a number of capacitors that are all in parallel with one another. Okay? Now, was that surprising to anyone? Okay? On one sense, maybe not, but in another sense, maybe it was. So far, we haven't done elements where, when they are in parallel, it's a plain old addition of the values. And with capacitors, it's parallel capacitors where you just add together the capacitance values. So that's kind of reversed from what you'd expect, like in a resistor or in an inductor that we saw last time. Okay? All right, let's do the series case. Any predictions about what we might have with the series case? Okay, let's find out. Okay, we'll do something similar here. Let's define a voltage for each one of these cases. Right, they have to be the same voltage and the same current as one another for the two cases. Okay, and if they are, then CEQ is equivalent to the combination of C1, C2, and C3 in series. All right. So where would you like to start with this one? What's a relationship we can bring in? I tell you what, I think probably the best place to start might be to identify that when you have a loop like this one, the voltage V is actually related to the voltages across each one of the capacitors. And in this case, the voltages are not the same for all of them, right? I'll call this V1, and let's call this V2, and let's call this V3. So the voltages are not the same across each one of the capacitors. But is there a relationship between the voltages that I've just written, V1, V2, and V3, and the overall V? Okay, Kirchhoff's voltage law says that V is going to be equal to what? V1 plus V2 plus V3. Okay? Now I'm going to make a little step right here that you may not know exactly why I'm doing it just yet, but could I take a time derivative of both sides of that equation? If I did that, on the left side, I end up with dV dt. On the right side, I end up with what? dV1 dt plus dV2 dt plus dV3 dt. Okay, and we'll pause on that for just a second, but this is an important thing to know that we can do that. What's a relationship we do have for a series circuit? We can't say all the voltages are all the same, but what can we say? The currents are all the same, right? So if we have I values, they are going to be the same regardless of where we look in this circuit, because there's no other place for current to go. So that means that if I look at my equation for each one of these capacitors, which, let's say for the very first one, we would say that the current through the first capacitor, which let me put that I1 at least for starters, is going to be equal to C1 dV1 dt. But we just said a second ago, it's the same current through everything. So instead of labeling that I1, what would you rather label it maybe? Just I. Okay? Now what if I take that little equation before I move on further? Can I solve that thing for dV1 dt? I can. dV1 dt is going to be equal to I over C1. Okay? Now, without having to write so much, can you see a pattern that would begin to form for the other capacitors? Okay? They each have I moving through them, and so dV2 dt is just going to be I over C2. And dV3 dt is just going to be I over C3. Okay? So that means that if I would care to, I can take my expression that I had over here with dV over dt, right? And I can say this is just going to be equal to I over C1 plus I over C2 plus I over C3. Okay? Now let me ask this question. I've been working on my circuit on the left. If I can move over to my circuit on the right, what's my basic capacitor equation for that circuit on the right? It would just be I is equal to CEQ dV dt. Okay? Or another way to write that is that dV dt is equal to 1 over CEQ. And everything has to be equivalent between voltage and current for these two circuits up here at the top in order for all this stuff to, in order for CEQ to become the equivalent of C1, C2, and C3 in series with one another. So what do you think I can do as my last step? 1 over CEQ is equal to, excuse me, I shouldn't have put 1 here. I knew something was not. What should I put there instead of 1? I. Okay, so I over CEQ is equal to I over C1 plus I over C2 plus I over C3. But what can I do with all those i's? Okay, if I divide through by I, then these do just become 1. That make sense? And once I do that, I can rearrange it one more time if I care to and say that CEQ is just going to be equal to 1 over C1 plus 1 over C2 plus 1 over C3. And so, just like in similar forms in the past, what happens if we put more of them in series? All we do is we just keep on adding terms in this pattern in the denominator up to however many capacitors that we've got. And so that is the equation that we use for combining capacitors in series with one another. Yes, sir? Yeah, so he wants to know if you just have 2 only that are in parallel with one another, can you do the trick where you just do the product over the sum of the values? And the answer is because the mathematical form is exactly the same as it was for resistances, there's no problem with using that technique. I could formally prove it, but it would look exactly the same as a proof of how you did the resistance, so I will forego doing a proof like that. Okay? Cool. You like that? Who wants to do an example problem? I see a lot of people excited and eager to do this example problem. Are you calling me a liar? Oh my goodness. I see one person who's excited about doing this example problem.